Hello, everyone. Welcome to the first main educational session on Nilearn. My name is Hao-Ting, and I'm going to be the host of this session. And with me is Yasmin. She is the core developer of this very awesome library, Nilearn, that we use in the neuroimaging community for like machine learning and like data processing. So this morning we will start with a very basic overview of how Nilearn deal with neuroimaging data, and then we will move on to some very simple machine learning model using neuroimaging data, all with Nilearn. So Yasmin, yeah, please take the stage. Go ahead.
All right, thanks. Thanks for the nice introduction. As Hao-Ting said, I help maintain Nilearn. I'm one of several core developers. Today, for this first part of the session, we'll go over how to perform functional connectivity analysis with Nilearn. And so I'm going to run through this notebook with you, and I encourage you to run the code along with me. I think you already probably have the link to the sessions in the notebook and how to access it. You can also just download it through here. So first, I'm just going to run this, and you don't need to worry about that. So what is Nilearn? So if you're not familiar with it, it's a Python library, open source, that we use to perform machine learning analysis when we want to work with neuroimaging data. So you might be familiar with scikit-learn. It's a quite popular Python library for machine learning analysis, which is used across many different domains. And it's a core dependency of Nilearn. And actually, the names might be reminiscent of each other because they were developed by the same team.
Yasmin.
And then, yeah, sorry?
Yeah, just to interrupt, can you zoom in on your notebook because people on site will be a bit difficult. And keep going. Yes.
Yeah, is that good?
Yeah.
Is that better? Yeah, sorry, I forgot to do that.
No, it's all right.
All right. Okay. So, so that's a bit about Nilearn, and then just to speak a bit broadly about machine learning analysis, I will run this cell, and we just here want to look at what our data should look like to make it easy to run a machine learning pipeline. And so you see that it's pretty structured, it's tabular format. And in the different rows here, you have different subjects, and the columns you have different features, including here some information from different regions of interest. So this helps us in terms of when we want to choose different features to predict to use in our machine learning models, as well as how we want to split our training and test data and so forth. So how do we get from our neuroimaging data to this kind of structural representation? So we'll talk a bit more now about what our neuroimaging data looks like. To explain a bit about functional magnetic resonance imaging, or fMRI. It's a neuroimaging technique that we use to measure brain activity, and the data is basically these 3D images or volumes. And we usually collect data at a given frequency or time interval. So we have several, many, could be hundreds of these 3D images. And you have the volumes represented in the spatial dimension by XYZ coordinates, and then you add the dimension of time to make it a 4D image.
No, there's no.
And so I'm gonna run this, but I won't go over this code. It's more just to create these images. and explain a bit more about the brain volumes. So the small units that make up the 3D volume are called voxels. So they have coordinates in X, Y, Z, and a certain resolution. Here we have 3 millimeter cubed resolution, and you can have several thousands of these that make up a volume. And with fMRI data, you measure the signal from these voxels across time, and this looks like what you see in this plot on the right. You have the bold signal, which I will talk about in a bit, where you have the amplitude of the signal, and you see this signal, how it develops over time. Here we measure time in seconds. And so to explain a bit more about this signal that we see, we're actually, we're not measuring neuroactivity directly with fMRI, but rather indirectly through the blood that delivers energy to neurons that are activated. And we call this mechanism the hemodynamic response. This gives rise to the bold signal. And just to give a bit more detail, so this activity creates oxygenated and like different ratio between oxygenated and deoxygenated blood. And this is what you can detect with the magnetic field. And BOLD stands for blood oxygen level dependent signal. So I'll also run this and still will not go over this code, but later we will get more into it. So this is just to simulate an event and show you what the response that we expect to see looks like. So here we have an event that has an amplitude of 1 and lasts for about 1 second. And you see that what we measure, the expected response, the hemodynamic response, looks like this. It has this shape. And so it peaks around 5 seconds, and then it slowly tapers off and goes back to baseline. So we need to take this into account in different analyses with fMRI.
Second seat.
But we won't really talk more about this. So with neuroimaging data, now we see that that we have to go from these 4D data to the structured tabular format. And so how do we do this when we have these kind of these spatial and temporal information? Before we get into that, it's also important to say that what you get with the fMRI data is not just the bold signal. It's not a clean signal. You have a lot of noise sources. A particular important one is head motion coming from the movement of the subject in the scanner. You also have noise sources from the scanner itself. So these are things that you need to take into account. And usually, if you're working with the standard machine learning libraries, they don't really account, or they're not designed to account for this. And this is really where Nilearn bridges the neuroimaging domain to machine learning. And so now we can actually start looking at some actual data. We're going to look at a developmental fMRI data set that is made publicly available by a group at MIT led by Rebecca Sachs. It's hosted on Open Neuro, but we took this data, pre-processed it, and downsampled it to make it a little bit easier to work with. So we will fetch this data in particular. So this data is a movie watching data set with 150 children and adults watching a Pixar film. And we're gonna just get the first 5 participants. So I didn't explain this before, but Nilearn ships with a lot of data, and as well as fetchers that help you download the data easily. It's publicly available data. So this is what we're doing here. We can set the data directory of where we want our data to be downloaded. Here's just my current directory, and it will be under the Nilearn data folder. And then I can use this fetch development fMRI method from the datasets module to fetch this particular dataset, and I define the number of subjects that I want, the data directory, and we won't worry about this for now, but maybe at the end, if we have time, we'll talk more about confounds. All right, so now we have this development dataset object, which has several attributes that we can look at. I will look at this one quickly. You can see what this looks like. So here at the bottom, you see like what the columns represent. So you have the first column is the participant ID. We have 5 participants here. We have age group, whether it's adult or child, gender, and handedness. And we can also get the path to the functional data, functional fMRI brain data. And here we see for the 5 subjects. And if we want to load an image and get some more information about it, we can use Nilearn image module, load image. And then here we're just selecting we're just indexing one of the subjects, the first one. All right, so here we see that we have this 3D structure of voxels, basically representing the volumes. And sorry. And we have 168 volumes, so 168 time points that we captured. All right, and here we'll look at some plotting functions. It's important to plot your and view your data throughout your analyses, just to make sure everything looks all right. And so here we'll use this interactive plotting function, view image, from the plotting module of Nilearn. And importantly, that since it's a 4D volume, we just want to take one volume, or we can look at the mean over all the volumes. So if you want to index, you can use index image from the image module, or here we'll use the mean image. So if I run this, we get something like this. And so I mentioned it's interactive. You can basically with your mouse just scroll around and look at different cuts of this volume. All right. So now maybe something is not rendering here, so maybe I'll go. Okay. Okay. So now we're going to talk about how we can extract data from the volumes and to help us to get it into this tabular format. And we can do this with the masker module of Nilearn. And to explain a bit how this works, we can look at this diagram. So if we want to define, we want to get information from regions of interest, we can define this mask, which is kind of like overlaying this 3D grid on the image. And we do we overlay a series of these grids over all the images over time. And we can just sample from what this mask covers. And we can get something that looks like this, where we have the number of samples in the rows, which is the different, representing the different images over time. and the features in the columns, which represents different regions of interest, for example. And so maybe I'll go back here. All right, so the masker objects that Nilearn provides basically help us do this. And we use these with different parcellations and different ways of defining regions of interest. Nilearn also, it ships with some of these, or it has fetchers that help to download these atlases easily. You can define your own parcellations, but we're not going to go over that in this tutorial. And so just as I mentioned, Nilearn provides access to several atlases, including Schaefer Atlas and the Harvard-Oxford Atlas. Here, we're going to work with the Multi-Subject Dictionary Learning Atlas, or MSDL. This is a probabilistic, provides a probabilistic maps of the brain, which I will explain what that means in a little bit. But here we can see that with the same datasets module that we just used to get the functional fMRI data, we can fetch the atlas. And then here we're just looking to get some information from it. So if I run this, I see that the atlas has 39 regions of interest. And here it's just giving you the main networks that make up these regions of interest. And so now we can plot it as well. It's a nice look at these regions visually. And so you can use prop atlas is specifically used to look at probability maps. So if I run this, it takes a little bit, I think. Maybe we can look here while it does that. And so this is what you will get. And you can see the different regions are outlined by these different colors here. And here is just to explain a little bit about the different types or ways that you can define brain parcellations. And this is important to know when you're working with neuroimaging data, just so that you know the appropriate, that you're using the appropriate atlas for your analysis. So there are functional and anatomical atlases. And so anatomical atlases are use the structural landmarks to separate regions, while the functional ones, like the one we're using, is based on the fMRI signal. And you get this through, for example, functional connectivity. And we also have distinction between probability and discrete or deterministic atlases. With probability atlas, you have probabilistic segmentations that use continuous non-zero values, and with the discrete or deterministic atlases, they use discrete segmentations where you have rigid boundaries. And you can find more information about this that goes beyond this. A really good lecture about this is done by Pierre Belec, and you can find it here at this link. I think I could switch over here. So yeah, this is the atlas that we loaded. All right, now we'll talk about applying the maskers. So you can use, depending on what you need to do, there's different maskers. A standard one is the Nifty masker that can be used if you have just one region of interest. When you have several ROIs like we do, you can use either the Nifty labels masker or the Nifty maps masker. And the difference here is just like what we just talked about between the probabilistic and deterministic atlases. So when you have the discrete segmentations, you need to use the Nifty labels masker. But what we have with the probabilistic maps, the probabilistic ROIs, we would use the Nifty maps masker. All right, and there's also throughout this notebook, there's links. You can find more information about all these different modules. You can even directly, maybe I can go to this quickly. Look at the API to help you know like which parameters you can use and what different options you have. And also, it's good to explore the Nilearn documentation. But we can also maybe go over that a bit later. All right, so now we can create a masker object. And so here we call the Nifty Maps masker, and we want to give it the MSDL maps. So MSDL Atlas that we loaded earlier has a maps attribute. It's the path to the Atlas file. Resampling target is just to make sure that basically the spatial configuration of your masker and your data are compatible. For example, that have the same resolution. And the trend is just typical method you can use to do some control for some scanner noise, I think, and just increase the signal to noise ratio. And so we call this, and then we call the fit method on it. If you're familiar with scikit-learn, you might have already seen this before. Here we don't provide it any data because we're really just we're kind of fitting the masker to our parcellation. So it's just to say that we're preparing our for our parcellation for our masker to extract the data from the right places. Okay. So now we can actually do the data extraction, the time series extraction. So here we call the transform method of the masker, and here we actually give it the fMRI data. Here is just from one subject. And if we run this, oh, I didn't run this. 1 second. Should have ran that. And now we can run this. And we get this two-dimensional data. And we see that now that we reduced our dimensions from 4D to 2D, and here we have the first dimension is now the time points, 168, and 39 represents the regions of interest. The 39 that maps we have from MSDL Atlas. And okay, I will again switch over here. Okay. So yeah, this is just to explain a bit that what we did with when we extracted the signal is basically for each region of interest, you sample just from that region, and you have, of course, this information over time, and you aggregate the information across the voxels in each ROI. So this is why you end up with basically just one piece of information, one value for each region of interest. Of course, you have this over time. And the dimensions are flipped. This is just to basically stick to scikit-learn convention, so that when you input information into models you use with scikit-learn, it won't mix up your dimensions. Okay, so now we can perform the connectivity analysis. So from past research, we know that sometimes cognitive functions is related to certain regions, activity of neurons from certain regions, and sometimes you have, of course, different parts of the brain interacting together when you perform a task. And this interaction is what lets us to describe functional activity as a network, the functional brain as a network. And to put it formally, the co-activation of different time series is called functional connectivity. And so what we do here is we calculate the pairwise correlation to get the functional connectivity. This is just one way to do this. But it's quite common to use. And so, yeah, we just see the pairwise correlation between the different ROIs. And we can use Nilearn connectome for that. We create a connectivity measure object here. And we choose the kind of method we want to use. And then we can call the fit transform, and we give it our ROI time series data that we calculated earlier. So I can run this, and now we can, a good way is to just look at this as a matrix, and you can plot it with a plot matrix from Nilearn plotting. And so this is what it looks like. And you see here the different areas, the regions of interest, and the correlations between them are represented by this color gradient where you have the positive numbers, it's like reddish, and negative blue. And we can also look at this as a connectome using the view connectome from plotting. So this is quite nice because it's interactive, you can move it around. You can zoom in and out, and you can also just look at the connectome by itself. There's some default views as well. And what you see here also is the different strengths of the correlations. And here it's grayed out. So there's a threshold here that we can use to just look at the correlations that are stronger than whatever threshold that we put. So that's why that's grayed out. And, if I increase it, then you would see less. All right. So we still have about half an hour, I think, right? So this is the last part where we'll talk about noise sources, and then in the end we'll have some exercises. And so here, so I mentioned a couple of times that there are several sources of noise that come from both like the subject being in the machine, but also from the scanner itself. So we need to take these things into account, and the Nilearn maskers help us do this as well. And so the development dataset object that we created also has an attribute called confounds. So we can look at this, and this is produced from doing pre-processing in fMRI prep. I didn't mention this before, but it's this was also done before by Nilearn developers and is available. So here you can look and see that you have several different sources of noise, including motion, head motion. And usually you wouldn't use all of sources of noise, you would just select a subset. So this is also comes back to that confounds, reduced confounds equals false that we saw at the beginning. You don't really have to worry about it too much, but usually we would actually want reduced confounds. And so here, to explain a bit more, that we had pre-selected some confounds. So we do have some new functions that were implemented, load confounds and load confounds strategy, that would help you select these confound variables so that you're not using all of them. So here, basically the only difference between the different steps that we did before is that you would give the confounds file for this subject to the confounds parameter when you call the transform on the masker. And then you would basically follow the same steps for getting the correlation matrix and plotting the matrix. So if I run this, so you can see it looks different than what we saw before. You can scroll back up maybe. It looks like there's like some more zeroed correlations closer to zero. And we can also plot it and see that we can see less of these edges connecting different parts of the brain. All right. So I think now we can take maybe 5-10 minutes to work on these exercises, and at the same time, you can ask questions. I don't know if there's already questions. And then I'll go over basically just some solutions for these quickly at the end.
All right. I think my camera is not on, but just give me a sec. Yes, my camera is on now.
Oh, yeah.
Yeah. Yeah, thank you, Yasmin. It was a great lecture.
Yeah, no problem.
I don't think the mic works for the room. So.
Oh, no, it's just off.
Yeah.
No, my mic on site was not working. It's just... Right, it should be working now. Oh, it's a 5. Go. I cannot really tell. Right, so now we have a few exercises.
There is one question, and maybe Hao-Ting, you're better equipped to answer it, but or maybe we need a more specific question. But I see here it says, "How do confounds work under the hood?"
Right, there are many things to unpack from this question. So I'm going to answer it from a more just a pure fMRI viewpoint rather than a software viewpoint. And so there are a lot of variables that will introduce noise to our signal, and we call them the nuisance variables. And although we have a lot of very complicated preprocessing methods for fMRI data, there will still be some residual signals there, and we will need to deal with them after some minimal preprocessing. So we will simply include those variables as regressors in a linear model to attempt to remove those signals. There are no best method on the market. There's simply no best method to remove the noise. We can only do our best to do that. Yeah, so from the fMRI analysis viewpoint, that is how it works. And if you want to understand how those related functions work exactly in Nilearn, I will direct you to the explanations we have provided in the documentation of the load confound function. Yeah, I hope that answers the question. And maybe, Yasmin, you can pull up the API.
Oh, whoops, wait. My scrolling is a bit off, so...
You will need to find fMRI prep. Oh, interface, sorry.
There we go. Yeah.
There we go.
Yes.
Hao-Ting, I don't know if you could use if you use your own microphone, because that thing's not working.
No. I'll explain that later. Sorry, you have some technical issue online. On site. Sorry, not online. Online, we're working very smoothly.
Seems good to me. So.
Yeah. So this is the function. So this function does one very simple thing, but it's actually extremely complicated. It will grab the variables based on what user wants to do to denoise their data from the fMRI prep output. This function doesn't remove the confound signals itself. It just makes sure you grab the correct things. Yeah. So if you scroll down a little bit, you will see there's a thing called strategy, and there are many strategies that you can use. And this is still quite complicated for machine learning researchers because you might not know the meaning behind all these variables. So that is why we have a separate one called load confound strategy. So this one, we just simplify the denoising method to 4 methods. So we have a simple method. Scrubbing, there's a typo I need to fix. And CompCore and ICA aroma. So these are the 4 main strategies that is available through fMRI prep. And that is that's 4 strategies that are very popular in the literature, and they all have their own strengths and weaknesses. Yeah. So if you want to learn more about it, I'm currently working on manuscript to make sure people have a direct reference using the fMRI prep confounds, because the past literature we have, all these confounds are benchmarked on a different preprocessing methods, and there's a chance that it doesn't apply to your data. So I'm trying to give user guidance on this one more directly interacting with fMRI prep. Yeah, so that's the very long answer to this question.
That's great, thanks. I'll maybe take the opportunity just for like a minute to talk about the website, maybe the documentation. Yeah. So yeah, API reference is really a great way to look at all the functions that are available in the different modules and get more information about them, what kind of parameters you can use, and more explanation for those. We also have the user guide. This split up in different sections where you can kind of get a guide into different types of analyses, different types of things that you can do with Nilearn. So some of the things we went over today, you can find more examples and more information about them in these. There's also example gallery also for each section related to the user guide, where you can find actual examples you can run all the way through to do like a full analysis.
Okay, we got another question. And this one is, what are development underscore dataset.func? How were they generated? I think we have a answer to this if we go to a website, actually. So if you go to dataset, just navigate. We need to navigate.
It's the first one. It's the first one.
Yeah.
Second one.
Development. Yeah.
I'm gonna click on it because it's easier to see it. And then here.
Yeah. So this .func attribute, they are just links to all the functional files. So if you go to return part of the thing, you will see it. Maybe Yasmin can explain this better than me.
Sure. I can even just maybe show it.
Yeah.
If it's easier. It just yeah. So if I look at development dataset func, I press enter. It's just you're just getting the path to the downloaded data, the actual images, and you can. And basically, what I showed in the analysis when I was inputting this data and using just one subject, you can just just index it and then work with data of this one participant. I hope that's enough, but if you have a follow-up on that.
We have one question that I've been ignoring in the chat, and I feel really sorry about this. Can you, we just want to show people how to download the notebook from the website. Yeah. So we go to the, so if you're on the main educational.github.io intro to Nilearn, if you go to any of the tutorial, and Yasmin will show us how to download it.
So for example, for the next tutorial, predict age from resting state fMRI that Hao-Ting will go over. If you just click on that, and then here you can download it in different formats.
And so
the IPython, so the Jupyter notebook is what you would use.
Yeah, that would be the simplest solution, I recommend.
Yeah.
Yeah, I hope that answers the questions in the chat. All right, we got some response. Thank you for clarification on .func attribute. I misread .func as functional and thought it was a signal, like a sine wave or some experimental simulation, so on and so forth. So when we are loading the data from Nilearn, usually from those dataset modules, the .func usually refers to functional data, and those images are too big to be stored, like to be loaded as a direct signal, like with some kind of binary format. So we are using a path directing to the file it is stored on disk. Yep, we have a question on site. Fantastic.
If you're doing parcellation with a functional atlas, then does it work in the way that it looks at the activation in the image that you give, and then tries to figure out the functional connectivities in the image that you're giving as input, and then kind of tries to apply that atlas on it? Or are the kind of parcellations or regions predefined and they like using functional connectivity from other RAID images, and then those are applied to the image that you give?
Okay, we have a fantastic question from on-site. I will try to repeat this question. So we have a student asking, what is a functional atlas? What does applying a function atlas actually do? So a functional atlas is an atlas that was defined from functional data. So they are predefined regions. And in Nilearn, when we're applying a functional atlas, what you're doing is you take the atlas and then you apply onto your data, extracting signal from those regions.
And it's applied spatial.
Okay, so the follow-up question is that applied spatially? And the answer is yes. Yeah. So this is why we designed this fun exercise for you. You have many different atlases you can access in the Nilearn dataset module, and they are usually used for generating tutorial and our test data. And they are both functional atlases and structural atlases. You can just load them and see what is the file like, visualize them. Yeah.
Just to comment that in Nilearn, let's define functional translation as well. So there are tools which you can take your data and try to generate parcels that are optimally adapted to your data. But this collection of atlases is pre-generated.
Yeah. So there's a follow-up and additional explanation kindly from Pierre for those folks who are online. So in Nilearn, there are also very cool functions. You can define your own functional atlas and from your own data. So you don't need to use those preset one that is provided from Nilearn datasets. Yeah, there are multiple options. Okay, we have about 10 minutes left for people to ask questions. But if people want to just go ahead and try out some of the tutorial exercises, that is very welcome. Well, I can see a lot of people in deep thought on site. And yeah, it's great to have you here, Yasmin.
Yeah, it's great to be here. Thanks for having me.
Yeah, and I hope this time it works kind of smoother on your side.
Yeah, it's fine. Yeah, unfortunately, I have to leave after this, so I can't stay for the rest. But it's totally fine. So.
All right. Yeah, I think we will let people to explore with the tutorial, and we will end the call with Yasmin. Yeah.
All right. Yeah.
All right.
Thank you very much.
Thanks, everyone. And I don't know if people Yasmin can hear, but let's give Yasmin. Yep, I think everything's working correctly on my machine. So fantastic. In the previous session, we had Yasmin talking about how to load data, like neuroimaging data from machine learning. And I hope that tutorial has shown that how complicated it is for machine learning, for neuroimaging data, comparing to the tabloid data you're more used to for machine learning tutorial or those online sites like Kaggle. What they offer is way more simpler than neuroimaging data is. So here we are going to go through a small age prediction model in combining Nilearn with another machine learning library, scikit-learn, to do this workflow. So I will talk about this research question a little bit first. So in the previous tutorial, we looked at the developmental data set in Nilearn, and that is a resting state data set with consisting of our children and young adults. So we are going to try to build a model to predict whether this subject is a child or an adult from the resting state data. So for the setup, it is going to be the same. We have learned how to load the developmental data set. And this time, if you didn't download the whole data set already, it will probably take a while. Sorry, Cream, we're going to clog your Wi-Fi. And there will be in total 155 subjects. I just realized I didn't clear the outputs of my cells, so I'm going to do that. And things will make a lot more sense. Yep, so meanwhile, for folks online, you're probably clicking through the cells and downloading data. But if you feel like you don't want to download data right now, you can just follow along and look at the website. On the website, all the cells should be rendered. Or you can look at the stream, because I have downloaded all data, surprise. Yeah, so we will need to download all the imaging data, and the confound data, we're going to use the non-reduced one because we might use it later. I forgot how I set up this tutorial. It's great. Yeah. So we have the prediction target, which is going to be the age category. In the data set we have a tabloid file detailing all the phenotype information of the subjects. And we need to look at it to see what is the potential category we're going to use and how it is stored. So there's a column called child underscore adult. So maybe that is one we're going to use. We're going to have a look. And yay, it looks like we have these two attributes stored under this column. So this will be our prediction target. And the next thing we're going to just have a look at how many subjects are there in these two groups respectively. So this is very interesting because for child we have 122 and for adult we have 33. This is a very unbalanced sample. This is something we can accommodate to a degree when we are training our model. But this is not going to be within the scope of the tutorial, so we are going to make the case a little bit simpler. To make this case simpler, we are going to just choose an equal amount of sample from the child category to match the adult category. So and we are going to do it in a very lazy way since there are 32 adults starting from the data frame and the rest that I know, because I know this data set inside out. We're just going to load the first 66 subjects and then take the information. Yeah. So that would be the bits that is usually more familiar with folks who has already done machine learning before. Then the next step we are going to do is to apply the masker function that we learned about in the previous session. So we are going to use, in this tutorial, we are going to use this very specific atlas. And if you want the publication associated with this atlas, I will recommend you to have a look at the documentation. And here I'm going to show you a trick on how to access documentations in a Jupyter notebook. So if you have a function over here and you just add a question mark after it and run that cell, voila, you have the documentation of this specific function and all details that you're using. So if you want to read a little bit more about this atlas, you can check the actual website and see the reference. Here we are only just showing the a tag over here. But anyway, back to loading the atlas. Yeah. So we're going to load the atlas with the nifty label masker function. And then we are going to calculate the functional connectivity matrix. So we will need to initiate these two objects for that to happen. So now, let's load all the data. So in this for loop, what it will do is it will go through each subject. It will first extract the time series and deconfound it. And I just realized this is a really bad thing. We need to reduce confounds. Yeah, because I should have looked at my tutorial material before. Right. So I'm loading the reduced confound because that is a pre-select set of confound variables, and we are not going to delve into how to select them in detail. So hopefully this will come out correctly. So what it does here is it first selects the time series of each subject, and then it will pass the time series to the correlation matrix generation function. And then we will use the correlation matrix over here. And this will take a little bit. Instead of if you have run this tutorial before, you might have already saved all those features in a file. So a lot of the time when we are working with more data than we have over here, what you would do is you will run these things in a separate workflow, and you will save that data out in some kind of format. Usually, I personally prefer just a text file, and then you can save it out and then load it afterward. So I will let people run this, and I'm going to cancel this because I've already run it at some stage, but it will be a wrong version of the data. Oh my god. Yeah. So I can load it over here, and for people can keep just running that cell. Yeah. Oh, I just realized I did something wrong. I need to run this. Sorry. Oh god. It's going to be fine. And meanwhile, we can go back to the website to show you what is going on. Okay. So this is a website render version. So if you finish running this function, you will see it will just show a string of text showing you all 66 subjects has been processed, can save them, and you can load them. And you will see the file we load, it will have 66, which is the number of subjects, and 2016, this is showing the number of edges in the connectome. Because in the connectome, there are 64 regions. And this number will be the number of cells in the diagonal of a 64 by 64 matrix. And you can plot them. So this graph definitely doesn't make that much sense. It is just a stripe of things. So you will have the subjects and number of features. And for feature over here, we are talking about the connectome edges. Going back to see, it's on 16. Right. All right. So the next thing we will need to do is to separate our data into the training sample and the testing sample. So it is very important that we want to make sure our machine learning training result can be applied onto a test sample that is not seen by the model. So here we are going to make sure two things that happens. So first, most important thing is we separate the data. And the second thing is we have two different kinds of classes in the data set. We have adult and child. In both the training set and the testing set, we will need to make sure the proportion of child and adults are equally represented. So here we can use a scikit-learn function called train test split, and it will be stratified by the class we have in the data. So here we are going to decide a testing data set size, and here we are using a 80% to 20% split. And if you want to understand more about all the logics behind why, more detailed reason why we need a training set, data set, testing set, I would recommend you to look at the recording of another parallel session we have this morning for the machine learning one, later. But here we're just going to show you the scikit-learn functionality for doing this. So now we can see after you split the 66 subjects, we have 52 in the training set and we have 14 in the testing set. Again, we want to make sure the number of adult and child are the same in both the training test and testing set. So we plot it over here. And it's very important to keep plotting your data while you're doing these kind of things for the first time, because things can go wrong. So that is what you will need to do for handling all the data. And the next step we're going to do is to run the model. So in this tutorial, we are going to use a very standard classification model called the support vector classifier. And this is a very simple and ambiguous, very robust model. We don't really have data for more complex model in this tutorial. So we are going to stick with this one. And there are some excellent resources you can check out during your own time to understand this model. So this is a very quick overview, a graphic overview of what a SVM do. Well, we are using a linear version, but let's classify it anyway. So assume you have two kinds of categories in your data set. What it is trying to do is to find the optimal boundary to separate those two sets of labels. And go read the paper when you have the time. So the first thing we will need to do in the scikit-learn interface is to define your model. And you might have noticed this is a very similar setup as when we are using the maskers, when using the connectome matrix generation in Nilearn. And this is a deliberate design. We are trying to make sure Nilearn use the interface style designed by scikit-learn, because it is a really good standard. We want to make sure there's less friction when people are using these kind of things. So first thing you need to do is to fit your training data into a model. So let's have a look at how this is doing. We're doing all right, and I don't know why I have so many. Anyway. Okay. So now we know how to use the code, and we are going to have a very quick overview about how does the model learns the data. And also, it's very important for us, the researchers, to understand if the model is performing in a sensible manner. So there are a few things you can try to understand from the result. you can see, first of all, the accuracy of the model. So this is a very straightforward thing. You just look at the proportion of prediction that was accurate overall. And the second thing you can look at is precision. And precision just means if the data that was labeled as one specific category are correctly labeled. So you will need to compare your prediction with the real label. And recall is just the number of true positives. So the number that are of one category and that are definitely true is predicted to be positive. And then you can calculate the F1 score, which is understanding a balance between precision and recall. So here is a really good visual representation. So precision is how many, so we can look at this diagram over here. So in this circle, this is the retrieved element. Amongst all the retrieved elements, the correctly categorized proportion will be the precision, and recall would be how many relevant items are being retrieved if by this model. So later we will see another graphic representation of this one. So let's train a model. And in Scikit-learn, we have a few other functions that is associated with a model class. So we have the prediction. So after you train a model, you can just put back in your training data and get the predicted label. So this is where you can understand how your model performs. And then another thing is you can calculate the model accuracy directly by passing the data and the training target and get an accuracy score. And you can even have a classification report and a confusion matrix to show the hit rate. And so basically another way of representing this circle over here. And we found something. So we can plot the accuracy. The accuracy is 1.0. It is a perfect classification. And for the confusion matrix, we can also see you're perfectly predicting adult as adult and child as child. Is this a good news? No, I see a lot of people shaking their heads in the audience. I'm really glad your intuition is so this is how you interpret this confusion matrix. So on the two corners, you have the true positive and true negative. Machine learning is amazing, it's perfect fit, right? But no, we have a very small sample, and this kind of situation is called overfitting, and we don't really want that. So how do you make sure your model is not that is not an overfitted model? So here we are going to introduce a function in Scikit-learn. Oh, my notebook has finished running. It's amazing. We can go back. Yeah, 66. Yeah. So yeah, the situation of overfitting, I'm really glad I see a lot of people in the audience shaking their head, because it is indeed a very bad thing. When you're overfitting your data, that basically means you can do everything perfectly with the data you can see, but when you're throwing any kinds of data that is outside of the training, you might run into issues. So in Scikit-learn, it is truly amazing. It has implemented a lot of functions for us to help us mitigate this without writing the actual code. So you can do something called cross-validation. So what it will do is, this interface is super simple. You put in your model, you put in your training data, you tell what are the groups are there in data, and you can specify how many cross-validation you want to do. So in this example, we are passing parameter of 3. That means you're going to further divide your data, into 3 sets, and you're going to, within your training data, you're going to see only 2 parts of that, and do a validation on the third unseen one within the training one. And then you can get one prediction result and one accuracy result for each set of cross-validation you're doing. So if we run that, we will see you get 3. You will have, so first fold, it is not doing so well. Second and third is doing better. So here you can just look at the overall model result. So here we have an accuracy of 0.96, because this sample we are looking at is actually quite small. So you see a relatively good prediction result. In real data, you might not see this kind of case. So for the same thing, you can calculate a confusion matrix just to see how does that distribute in this cross-validated version of the model. So we don't see a perfect prediction. This is usually a good case. So there's another thing you can do is to look at the neural model. And how Scikit-learn implement this is a permutation test. So if the class is balanced, the chance level is close to 50%. That means you present one subject to the model, there's a 50% chance it will be classified as a child or an adult. And it looks like we have a p-value that is below 0.01. So that means it is performing really well, and it has a good accuracy based on the model. If you want to have a look at how permutation test and cross-validation actually work, you can go onto the Scikit-learn website. They actually have really good tutorial on explaining this. So this is how the basic interface of a model works. So there are other things that we haven't covered. So there are a lot of parameters in a model. Right now we are just using one set of options, and there are things you can tweak. And all these are tweaking on the model. You should be doing that on your training data only, and you can test a multiple tweaked version of the model, applying on the training data, and decide what is the best way to tweak it. I'm not going to cover how to compare those ways of tweaking them and how to quantify them at this session specifically, but you can read a little bit more. I have linked the relevant material down in later part of this notebook. So this call so the first few things we can do is this. Here we show an example of scaling the data. So this is one thing we didn't do when we were going through previous part of the tutorial. We didn't scale our data. But this is actually a quite important thing to do, because sometimes your data are dirty and they are on an uninterpretable scale, and we want to make sure they all fit onto a standard scale that we can better interpret them. So this is what we normally do. So this is the original data. It was on a scale between 1 and -1. So I know what does this value means because I've been working with functional connectivity data for a decade. This is between 1 and 0 because this is a Pearson's correlation value. But this is not a very universal way to look at all data. So what we do a lot of times to scale it and make sure it is on a z-score scale. So that means the data will have a mean of 0 and it will have a standard deviation of 1. So here is the scale data, and you can see it will be fit onto a different scale. And for a standard deviation of 1, that usually means 65% of, that's where you down to 65% of the data, and to cover all the variance, it will go up to 4. Yeah. I'm not teaching stats over here, so I will skip that. Right. And then after scaling your data, you can repeat these same things we did. We cross-validate to your data on the training data on the model. You get an accuracy score, and then you can get the confusion matrix. And yeah, it looks like scaling the model didn't change our prediction result that much, but because we have for the neural imaging data, they're actually relatively clean because it came from pipeline that we know everything is in the functional connectivity matrix. Scaling over here is not going to change very much. So yeah, how do you think about the result of this model comparing to the non-transform model? Not very much, because it's already all right. It's already on a standard scale, let's put it that way. And there is another thing that we can do in order to tweak the model. It is not adding steps into your workflow, but just tweaking the parameters in your model. So for example, in this very specific case, in a support vector classifier, there's a parameter called kernel, and you have a selection of kernels that you can use over here. So yeah, we can play around with that later yourself. I'm not going to run that over here because we're already training a model. So now we are going to look at our test data that will be put aside for this whole time. So what you're going to do is you're going to pass your test data to the model you just created with the cross-validation result. And because our data was scaled in the training data, so you will also need to remember to scale your testing data. And then, yeah, we are going to run all the same thing on the. So we're going to fit the model. I'm just going to run that. We're going to fit the model again with our training data that are scaled, and we are going to generate the prediction and all that. So here, this is the result. We are very familiar with the accuracy and confusion matrix at this point. So this is the result on your test data with 14 subjects. It looks like our model can perfectly generalize our test data. This is fantastic news. Yeah. But so this shows that our trained model on our testing data can capture some certain feature that is related to age in the functional connectivity matrix, and that is confirmed by our label that was labeled by the researcher when collecting a data set. So one very common thing, after you do all these things, you look at the accuracy, you look at the confusion matrix. One very common question neuroscientists ask is, how do they interpret this machine learning model? Because they are not just interested in if a model can predict the result. They want to know if there are something that can contribute to a theory. So how to interpret a model that you train is a very big topic in the field. And here is like a lot of active research on this kind of thing. The simple answer to this very complicated question is we don't really know what is going on. It's very complicated. And there is a paper, a tutorial blog post I'll direct to you to read as extra material over here. So there is a way to access things that's in a secular model. So it is the coefficient attribute over here. And you can run it, and you can see a bunch of numbers, and can visualize them as well. So it will take some time to run this cell. Yeah. So because we had, in our data, we have confunctional connectivity edges, and there are 2016 of them. So you will have 2016 of that. And yeah, and it is still running. Yeah, oh yeah, over here. So you have 2016 features, and each of that is going to have a weight. And this just shows up it is positively or negatively contributing to the model when you are classifying the results. So there's another thing, because these features are nodes on the functional connectivity matrix. And there's a very sweet feature in the Nilearn masker, which is if you put in something that is the shape of the connectivity matrix, it can inverse transform it to make it a functional connectivity matrix that is a more familiar shape for you. So we can use this inverse transform function from the functional connectivity objects we used to transform our data earlier. And you will get back a 64 by 64 matrix. This is something that is much more familiar with us. So now we can visualize them. It will take a little bit of time, but it's going to be fine. Yeah. So I'm going to zoom out a little bit so folks on site can see. Yeah. Oops. Yeah. So here, this is the functional connectivity matrix, and we're only plotting one off diagonal over here. You can play around with the plotting function later if you want. So this is, so here we have the feature importance bar graph, color bar graph over there. And we transform that into a functional connectivity matrix with the edges on the off diagonal. So this is something that people who work in neuroimaging data are a little bit more comfortable with. And we can use the plotting function from the previous session to put it back onto a real brain. This is very exciting. So I'm going to wait for a little bit. So what it will do is we have a function called find parcellation cut coordinates. So if you pass a atlas to that function, it will find out what is the centroid of each parcel, and then give you a coordinate. So you can later plot it onto a brain. We'll just wait for a little bit. Or, meanwhile, we can go have a look on the website. So yeah, so we have a really pretty transparent brain, and you can plot all the edges on them. And I will explain a little bit why this looks a little bit wonky. So first thing, why are all the centroids on the left side of the brain? This is actually because of the nature of the atlas. The atlas we use is not an atlas giving you standalone parcels. So this mixed atlas, they actually give you something, it's more a resemblance of a network. So actually this function don't work very well. In my own paper, what I did was I further break down each parcels that was defined by, so one of the 64, into individual regions. And with that kind of case, the representation on the graph will be a little bit more accurate. You will not see everything being plopped onto one side of the brain or things like that. But for the purpose of tutorial here, just to show how visualization works in Nilearn. And another problem we have with this graph is there are so many edges. What are we going to pay attention to? So there is a really nice feature that Yasmin has already showed us. You can put a threshold onto this map, and then you can just isolate out the more important edges. And of course, we have the fancy interactive view of this. And yeah, oh yeah, it's working on the website. It's just a little bit laggy on my machine right now. Yeah. And there's another function you can try, which is you can have this figure as a HTML file and just open it in the browser. So that concludes this part of the tutorial. And there's a lot to cover because we're trying to cover some basic machine learning and some other information of like scikit-learn interfaces and stuff. So there's quite a lot in this notebook. But one of the exercises I will give you is how are we going to pull out the code from this notebook and compile just one correct version to run this pipeline. So for example, in the beginning, we have done one thing. We trained the model with all the data without cross-validation. We want to exclude that part if you want to have a piece of code that is actually working for your research. And it is very common for people to develop their pipeline in a Jupyter notebook. So the skill to port those information from a notebook into a script that can be cleanly executed is a very important skill. So this is one thing I would encourage you to do, although this is not directly related to machine learning, but it just as a general research skill, this is going to be very important. And second thing is, I have briefly talked about the problem of this atlas. So maybe one simple solution is we can find a different atlas that has just a isolated parcels for each dimension, and that'll be easier for you to understand. So you can maybe find another atlas to try that. And the third, more advanced practice I will give you is try to implement different atlases as part of the hyperparameter tuning that I briefly mentioned before. So there are parameters in the models you can tweak, and you can even have how you do the feature selection as part of the hyperparameter tuning. So I would say leave this one until a later date after you understand how model selection works better to try it. And if you want to have a read, scikit-learn does have like a page, and they have functions to help you cover these type of things. Yeah. So that concludes the lecture part of this tutorial, and now we have half an hour to play around with everything that is being covered. So yeah, I will start to take questions from Crowdcast and from the crowd. Are people having fun on site? Make some noise. Right. Okay. Right. From the look of the Crowdcast chat, there is no immediate questions. But okay, we have a question on site.
So the connectome at the end there, what does that mean?
That is a great question. I have no idea.
So there's a link for and
yeah, so
are those the same plot as the
yes, so the question is for people who are tuning online is, what does this plot mean? And is this, so this is just plotting everything you see over here. In one sequential order.
These are the weights that the model decided on.
Yes, these are the weights the model decided on.
It's like this edge is more important. Like I can focus on this edge. It's decided this person is the outer.
Let's put it this way. So the question is, does this graph shows it means like there are some edges that is more important, we should focus on them? Is that
for like it's also with reference to the entire atlas?
Yes, so that's what the model decides, if this edge is more important for deciding is a child or an adult. Yeah.
And so in the plot, in the technical plot, that means that it's saying that the left side of the brain is more distinguishing.
Oh, okay, so the question here is, how do we interpret the last three plots all together? And I can tell you, so does this mean the left side of the brain is more important? The answer is no. The reason of why you're seeing it over here is it is an error by the atlas design. So what I can show you over here is actually just plot the atlas a little bit so you can get a better idea of why this is happening. So we have I don't remember how we call the atlas file name. I'm going to do live coding over here. This is very, very scary because you should never do this. But I'm going to do it because it's fun. So first thing I'm going to do is from Nilearn the image. So I'm going to just plot a few slices, not slices, just a few ROIs to show you what is actually happening with this atlas. So we can use the Nilearn module image, and there's a function called load image, and we can use that. So I'm just going to give it a very explicit name of what it actually is. It is the missed atlas. And so the shape of this thing, if I remember it correctly, this is just a 3D. This is just one volume, because this is this specific type of atlas is called discrete atlases. So that means each RI is a very discrete cluster, not region, a cluster. And how they are usually stored in a nifty file is they put it on one volume, because all these RIs don't overlap with each other. So here comes a great question. We only want one. I'm only going to show selected ones. So what I'm going to do? Luckily, Nilearn image has another great function, because Nilearn is so fantastic. I just feel like I am doing a commercial selling this product, but it is truly amazing. And I have to say, during the start of my PhD, I was only using the masker functions extensively in Nilearn. I didn't know you can, for example, if you want to just get the same value, so how they are labeled is, if it's ROI number 1, it will have a voxel with the value 1 in it, and you're going to filter that. So what I did in the past was I would use another software to break down all those information and then load them again. But you can actually do them all in Nilearn. So you have a function called index image, and we can have a look at what it does. Index image. Oh, this is for 4D. So this is for slicing 4D data into 1D. But what we have, this is on a time and dimension, this is 1D. So there's another function we can use. It's called math image. Actually, let me have a look at a Nilearn website. Maybe it has a better function. Well, I don't know, Alexi, do you know there's a better function? Yeah, for thresholding. So if you only want voxels that have value with 1, I think it's just math. Yeah. Yes. Yep, because I still don't know everything of this thing. Okay, so this is why we need an awesome website, and that is easy to navigate. And we have an awesome website. Just look at this beauty. Right. So we have math image reorder threshold image. So this is what we want. You have you can cluster threshold and then okay. I'm going to use this. Threshold image, and I'm going to set the threshold I'm going to set a threshold because it's just only discrete. I'm going to set the threshold at 1, so it will give me everything that's labeled with 1. So great name, ROI1. So usually because I'm a very skeptical person, I don't know what am I doing. I want to make sure it's doing what I want to do. So first thing I'm going to check is this actually something that only contains 1 and 0? So you go to object, and that is or did I spell it wrong? Yeah, I'll just do np.unique. But oh, great. I'm totally not doing it right. Ooh. Or should I just use math? Well, I don't know. I will just show you the simple way.
You got the data, right?
Yeah, I got it. Yep, and you can.
Say ROI was on data.
Exactly. Fantastic. So say we want everything that's 1. Let's do that. And you'll get a binary. Yes, so what I would do over here is, first of all, I haven't done this for such a long time. NP done.
But I usually you just provide that formula, and sometimes you generate an image that directly, because here you only have an array kind of something. Okay.
Yeah. So what you will do is, so Nilearn image actually has another function called, I think it's make new image, something, I forgot the actual name, but what it does is, it will take that kind of array information and you can just make new image like. So you can pass a reference image and you can pass the data that we just created, and then it will return an object for you to plot it. So new image like. So I'm going to first of all do this new image like. Because ROI1 will be this binary value we just see, and then we have new image like. And what I'm going to do, I'm going to use the original MIST atlas as the reference image, and I'm going to pass through the data of ROI1. I'm going to call this me ROI1. And now we can plot it. So use the plotting function dot plot ROI. Yeah, and by the way, this is a fantastic feedback from you, because next year we know how to improve this one to make it like more sensible. So here, this is ROI number 1, and as you can see, it is not a isolated parcel. It is actually things that are on both left side and right side of the brain. So I don't know exactly how they decide the coordinate, if this is the case, in the cut coordinate calculation function. But this is why you get one key result in this plot anyway. Because you see, this is I was just going to explain what this cross does. So this cross is also generated from the same function, this fine parcellation cut coordinate. And it just decided it's going to be on the left side of the brain. Some people in the audience will know better than me why it is like this. I don't know. And they don't know either, right? So, yeah. So you just decided the centroid of this specific ROI you're seeing is on the left side, and that's why it boom, put a point on the left brain. This is not great for plotting.
Yes.
This kind.
There is a region extraction function somewhere in the library that can separate ROI from the predicted regions.
Yes, so we have some fantastic addition from Bertrand. There is a separate ROI function in Nilearn, and I can probably find the relevant tutorial on the fantastic Nilearn website. I remember it is separating the yellow atlas. I have no idea, actually. I'm going to use the fantastic search function and use the worst keyword. Oh my god, look at this. Breaking an atlas of label in separate regions. I cannot believe that keyword works. So yellow atlas is a very popular atlas in the resting state literature. It parcellates the resting state brain based on connectivity features into 7 networks. So yeah, if you just load the original one, you will see 7 big chunks of brains. And this tutorial is just showing you can relabel that into separate regions. So it will give you 49 of them if you do this. But yeah, there are many other atlases that's also defined in these kind of manner, because it doesn't necessarily need to be a isolated region. It depends on what kind of information it wants to show. So sometimes it will just be a network like this. Depends on how you want the cluster algorithm to work. So yeah, so if you really cares about the connection of like a very localized brain region, you will need to pass through this kind of separate function to separate the ROIs. But it is a perfectly valid analysis choice to use the signal from a network. It is perfectly fine. Because in that case, that means the feature you're interested in is the collective feature within that network, rather than a very local region. The reason they are put into the same ROI as a network means based on the algorithm the atlas creation was using, decided all these voxels has similar properties are equally important in that manner. So that's why they are put into a network. But I understand especially for cognitive neuroscientists, you probably want to know more about what a single brain region does, then in that case, it will make more sense to separate them out as isolated regions. Yeah. So they're both perfectly valid choices. It's a great question. Thank you very much. And I'm going to go back to Crowdcast and check how are they doing over there. Yes, I will repeat the on-site question over here for the online crowd. So the on-site question was looking at the connectivity graph we show in the glass brain. At the very bottom of the tutorial, it looks like all the connections are very biased onto the left side of the brain. And does that mean the left brain is more important? The answer is no, and the reason is because of the atlas we used. So now you can wind back when you're looking at a recording to understand why does that happen. And I'll probably write down the more precise answer in Discord channel, and we will update the tutorial accordingly. So yeah, basically it depends on your choice of atlas. Some atlases just includes regions that are widely spread across the brain, and you cannot really find a good cut coordinate for that. Yeah, we have another question on site.
Confounds, are they nodes?
Okay, we have a philosophical question from the audience. Confounds, are they noise? The answer is it depends. So there are some certain sorts of noises we decided that we're not interested in them, and that's why we call them confounds in that context. Yeah. For example, we want to know about the brain activity, and we know the data is contaminated with motion. And if you don't want motion, you just try your best to regress them out. And there are other types of variables, like a more controversial one, for example, would be physiology signal. So for some researchers, they want to regress out the physiology signal. But if you know how fMRI data is collected, it is actually heavily dependent on the physiology of our brain. So those two signals are entangled together. There are people who would advocate for regressing them out, but some people, if they want to understand how those signals intertwine, they probably will not deal with it very much. Yeah. But there are definitely some very common types of source of noises that we regress out. For example, one is instrumental noises from the scanner, and usually we handle that with a filter. So I am going to go to one Nilearn function to help me explain this to you. It's called signal. And clean signal. Yes. So in this function, it handles the signal and other type of noises that you decide as a researcher. I'm not going to decide that for you. How are they going to be handled, and this is curated based on literature. So first thing we do is detrend. So that means your signal might drift in a certain direction, and we just want them to be more centered. And we have high pass and low pass filtering. So this is a common method to deal with instrumental noises we have in the signal most of the time. And then we have remove confounds. So this is a more like a vaguer category. So you have, for example, you have motion. We keep talking about motion, and that is one thing we regress out. And there are some other type people regress out. For example, when we are looking at brain activity, people are mostly interested in the recording in the gray matter. But in the brain signal, we don't just have signal from the gray matter. We also have the white matter. We have some spinal fluid and all that kind of things. And they can all interfere the activity recording of like neighboring brain regions. So what people do a lot is they use a mask to extract the signal from, say, white matter, and then they regress that average signal away from the gray matter signal. And we have talked about standardizing your data. This is especially for raw neuroimaging recording, because that is I would definitely recommend you to look into the textbook definition of these things a little bit more. But the basic understanding is what we are actually recording with a MRI machine when we're looking at functional image. It is an estimate value. It is a statistical value. It is not a true value of what is going on. So from different scanner, you can have a different like set points, and that's an arbitrary. That is something on the arbitrary scale. So we need to standardize it. Yeah. And and if you want to understand a little bit more about confounds, I'm going to shamelessly self-advertise. If you want to understand a little bit more about the confound that is coming from fMRI prep, this software specifically, you can have a look at this website that explain a little bit what are the different types of variables and how they are mapped onto the low confound function on Nilearn. So this is one source, and I would definitely say for the too long didn't read version, just go onto the Nilearn website, go to interface and fMRI prep over here. Yeah, so that's one very long answer to your question of what is confound.
Are they included with the data, or are they computed?
Okay, so the other question is the confound included in your data, or are they computed separately? So if you mean, is it in the signal, then yeah, they are mixed together.
No, I mean like the data set, when you look at the data set, is that like a separate part of the data set that has been pre-computed and you just load it, or is it you compute it on the fly when you load it?
Okay, so the question is whether Nilearn function loads the confounds as a separate file, or does it calculate on the fly? The answer is they are pre-compute information, and you load that when you load the developmental data set, example data set. The reason is they are just something simply too computationally heavy to be computed on the fly, and there are things that you can compute on the fly, but when we are doing this tutorial, we have them loaded from the confound function. And there's a function in Nilearn, actually, if you go to the signal module, there's a function called high variance confound. So what I explained was one way of classifying confound, and in Nilearn there's another way of doing confound. So what it does is it finds the high variance, it creates a mask on your data first, and they highlight the voxels with high variance, and then they extract all those signals and do a principal component analysis, and use that to approximate the noise in your whole data and then regress that out. Yeah, so this is another way of doing it.
Usually, if you don't have the confounds providing with the data.
Yeah, so just for the online crowd, this function is very useful for a case where you only have the data, but you don't have the confound file coming with your data. And this is a definitely valid scenario that you can encounter when you're working with data that is in the wild internet. And you just found some data, and all it says is processed, and there's nothing extra with it. Then this kind of function will become very handy. That's a great question. Thank you. And I'm going to check in with the crowd again. I just realized my face looks super red on this camera. Yeah, oh, looks like we have 3 minutes before lunchtime. Fantastic, guys. You use questions to fill out the time. So I think we will conclude this session. And thank you for the online audience to tuning in. And there are a lot of more exciting sessions for the afternoon, and please tune in again. Thank you very much. I'm going to disconnect.
Thank you.